Hello, everyone. Welcome back. This is the second half, second part of our opening speech and IKX talks. So now I will invite my guest host, a superstar in high tech, and recently you read most of his papers. Xuanhe Zhao. Now, Xuanhe, please. So.
Hello, everyone. Xuanhe Zhao from MIT. This is really a great pleasure and a great honor to co-host this ICANX talk series. We just heard a wonderful talk from Professor John Rogers. It's always challenging to give a talk after John, but if I can think anyone who can give an excellent talk after John, one of the few names pop up to my mind is Jun Huang. Professor Huang is a chair professor from Duke University. His research area is combining acoustics and microfluidics for impacts in medicine. He's the leader and the pioneer in this field. He won a long list of awards. I wouldn't, say them one by one, otherwise it would take probably 1 hour. He also been, fellows and members of many societies. So without a further introduction, I give you Jun Huang.
Xuanhe, thank you very much for your very, very kind introduction. I'm great honored. I think it's impossible. It's impossible for anybody, especially me, to give a talk after John. But Alice assigned me to do that. I have to do it. So first, I want to thank Alice for giving me such a wonderful platform to give a talk. I've never had a chance to speak to 8,000 people. It's my first time ever. And I want to thank Professor Zhao for your very kind introduction. Especially, I want to take the opportunity to thank all my friends and colleagues in China for the help over the years, especially for recommending students to me. Over the years, I have very, very good opportunity to have wonderful students. And a lot of the students from mainland China, and the first student who worked on the topic I presented today, Acoustofluidics, Jun Huang. Actually, he's a student recommended by Alice. Thank you, Alice, very much. And Jun Huang was really a true superstar in my lab. And whenever I give a talk, I say that I only recruit 2 kinds of students. The first kind are the students and postdocs who are slightly better than me. The second type are the students and postdocs who are a lot better than me. And the majority of my students and postdocs are the second type. And when I say that, a lot of people were laughing. They think I was joking. I want to let you know that I'm not joking, and I'm dead serious. And indeed, I would say every single one of my students and postdocs are better than me in some aspects. Some of them are better than me in every single aspect. And also, a lot of my former students, they also went on their own academic career, become professors in different places in the US, in Europe, and in China. Quite a few went back to China. So, yeah. So today I'm going to share with you our work on acoustofluidics, which means the fusion of acoustics and microfluidics. And we mainly do it for biomedical applications. So before I share with you our work on acoustofluidics, I would like to share with you a fine example of acoustofluidics. When I was a college student, I was a big soccer fan, and my favorite soccer player was Roberto Carlos. And he is very good in doing free kick, especially bended free kick. So now I'm going to show you a bended free kick he did in a match between a Brazilian national team and a French national team. So Roberto Carlos put the soccer ball on the field, and he ran and he kicked. So it's a bended ball. It's a curved ball. So let's watch this video again. So whenever I give a talk, I always like to show this video. And very often when I show this video, and after my talk, the only thing people remember is this video. So, I say, why do I bother to show other part of my talk? I just show this video. So people who do microfluidics, like myself, my students, there's no way for us to do such a beautiful bended free kick. But we can do something that Roberto Carlos cannot do. So this is a microfluidic chip that mimic what was going on the soccer field. And this is a water droplet that mimics soccer ball, and each triangle represents each Brazilian player, and each circle represents each French player. And there's an acoustic transducer here to drive this water droplet. So you drive it along a curve. So I want to say that so this chip is very expensive. Actually, to make this chip takes a lot of money from the government, but it doesn't do anything useful. But it has a very important take-home message, and that take-home message is that if we do it right, if we control acoustic field right, if we control the flow field right, we can precisely manipulate fluids or particles inside fluids in a precise, programmable, and contactless manner. Contactless means you can, without physical touch. So in Chinese, we can say 隔山打牛, right? So you can basically, 隔山打牛 means you can kill a cow. Basically, you are on one side of the mountain, but the cow is the other side of the mountain. You can kill the cow. Your power can go over the mountain and kill the cow without touching the cow. So that's the nature of acoustics. We can do all the sort of manipulation without touching the objects you are manipulating. So acoustofluidics is still a very new field, and but I would say in the last 5 to 10 years, really, I think a lot of things are going on in this field. You can see the number of papers people publish in this field in the last 4 years actually is already more than the previous 15 years. And we also read a review in this field, and we hope that our review and other review papers in this field, research articles in this field, can encourage more people to work on this field. Because we really believe that in the field of acoustofluidics, there are a lot of things has not been explored, either physics or engineering or biomedicine. I think a lot of things can be done and has not been done. And I think it doesn't matter whether your background is physics, is mechanics, is mechanical engineering, electrical engineering, biomedical engineering, chemistry. I think that certain things you can contribute to this field, or biology and medicine. So our group, we have been trying to assemble an interdisciplinary team, try to address all these problems, from physics to engineering to biology and medicine. So sometimes we call our technology acoustofluidics. Sometimes we also call our work acoustic tweezers. Acoustic tweezers, we get the name from optical tweezers. Optical tweezers has been a very, very powerful tool, and it has impacted so many researchers in the last 40 years. It can precisely manipulate particles or biological cells. But optical tweezers has 2 drawbacks. Number one, the system is tend to be very bulky, very expensive. It's difficult to maintain. Number 2 drawback, optical tweezers, because they use very high power laser, they tend to damage the particles, especially the bioparticles such as cells. So we think it's very important to develop alternative technologies that can address the drawbacks of optical tweezers. So that's why we are developing acoustic tweezers. And acoustic tweezers, we have, so again, I want to use an example which has nothing to do with acoustic tweezers to illustrate why doing acoustic tweezers makes sense. So I think all of you are familiar with ultrasonic imaging. Ultrasonic imaging is not the most powerful imaging technique in the world. It's not the most powerful, most high resolution imaging technique in the world. However, if ultrasonic imaging can get the job done, almost everybody would like to use ultrasonic imaging for 2 reasons. Number one, ultrasonic imaging is very compact and very inexpensive. Number 2, ultrasonic imaging is very, so it's very small. It's very small. It can, the nurses can put into their pockets and move from one room to another room. So it's really point of care devices. It only costs a few $1,000, $10,000. It doesn't cost $500,000. The second point is even more important. Ultrasonic imaging is very safe. It's very gentle. It's very biocompatible. It does not So I have three beautiful children. And whenever my wife is pregnant, what did doctors use? They use ultrasound. They didn't use X-ray or big laser or big magnet or big electro. And when doctors using ultrasound to scan the baby, I totally have peace of mind. I know, I don't care whether doctors using ultrasound for 10 seconds, 20 seconds, 1 minute, or even 5 minutes. We know it's a very safe technique, has been out there, used by half of the population in the whole world for half a century. Pretty much no side effect ever reported. So if we do it right, we will have, and our acoustic tweezers will have basically very similar power intensity, very similar frequency as ultrasonic imaging. So if we do it right, we will have the two advantages as ultrasonic imaging. Number one, very compact, very inexpensive. Number two, very biocompatible. So because our acoustic tweezers have many different mechanisms, so today in my talk, I will not talk too much about mechanism. I will mainly talk about applications, what these acoustic tweezers can do. I will just use one slide, very simple slides with no equations to talk about the mechanism, very simple mechanism, one of the simplest mechanisms. So if we have two interdigital transducers, each one of them can emit surface acoustic wave. So these two surface acoustic waves will meet each other and will interfere and will form standing surface acoustic wave. So there will be pressure nodes, which is the lowest pressure points, and the pressure antinodes, which is the highest pressure nodes. And the biological cells will tend to migrate to the pressure nodes. So by forming a periodical distribution of pressure nodes, we can form a periodical distribution of cells. So that's the basically fundamental working mechanism. Device work as expected. So when the acoustic wave is off, we can see the particles or cells are randomly distributed. Once we turn them on, we can form pattern. We can form one-dimensional pattern or two-dimensional pattern. We can turn the pattern on and off. We can also change the pattern. We can also use our tweezers to control a single particle, a single cell. So imagine if we inject a sample solution with cells or particles into a microfluidic channel, and we turn on acoustic wave. We turn on the voltage, acoustic wave is on, and then we can trap a single particle, and we can move it. Now I'm a professor at Duke University. Before 2016, I was a professor at the Pennsylvania State University, PSU. That's why we are writing PSU. We also read something more complex, and that was the first journal we submitted our paper to, and it was declined. So we changed one figure and submitted to a different journal. And so the point is not to please the editor. It's important to please the editor. The point is when we write PSU, we only need to write along either x-axis or y-axis. But when we write either Nature or PNAS, we have to write along tilted lines or curved lines. We want to showcase if there's a need to do that, we can do that. And of course, we moved to Duke. We want to write something Duke, so to make our dean and the president happy. So far, I give a few examples. Again, as I said, I go very little into mechanism. I just mainly showcase what this technology is capable of doing. I showcase a few examples that we can manipulate cells or they are micro-sized particles. We also can control nanometer-sized particles. In this case, we can control 28 nanometer polystyrene beads. When the acoustic wave is off, they're randomly distributed. Once turn them on, they are concentrated. We can also do all sorts of things with particles down to 10 nanometer. And we are trying now to push to 1 nanometer or even smaller than that. And this is possible. So we can not only control particles in the size of micrometer scale and nanometer scale, we can also control particles bigger. Actually, acoustic wave works very good, very well when the particles are bigger. So this work we are controlling C. elegans. C. elegans, a very important model organism, has been used a lot in biology. So it's a worm. So we can trap a worm, and we move it down, and we move it left, and we move it down again. Right? And we also can stretch it. So, and after we torture this worm for an hour using acoustic wave, and we release the acoustic wave, these worms are still happily swimming. So we know that they're very, very happy, and our work, our tweezer is very gentle. So we can not only do translational movement, but also we can do rotational movement. We can rotate in XY plane. We can rotate in XZ plane. We can also rotate not only biological cells, we can rotate C. elegans, from micrometer scale to millimeter scale. So we can not only manipulate particles inside fluids, but also we can directly manipulate fluids itself. So we can do mixing, we can do pumping. I just want to say that I think I'm very happy to listen to Jun's talk. I think his work really take microfluidics to a different, totally different territory. But I think Jun is totally right. Microfluidics field has been out there for 20, 30 years, has a lot of problems. I think one of the problems is we still don't have a good fluid manipulation techniques. Right? So the syringe pumps are very precise, they are very reliable, but they are expensive, they are very bulky. The paper microfluidics, they're very cheap, they are very simple, but they are not very reliable. I mean, you cannot use it to do complicated fluid manipulation. So what I'm saying is our acoustofluidics, we can do very complex, precise, reliable, controllable, programmable manipulation. At the same time, the device is very simple. We can just need one layer microfluidic devices with a transducer, which only costs, if we buy it from Radio Shack, it only costs $1. If we buy it from eBay or Alibaba, it only costs 25 cents. So we can have the benefit of both. Very simple, very inexpensive, at the same time, very precise, reliable, and controllable. So this one shows that when we use two pipette tips, one as inlet, the other one as outlet, right? So, and we turn on the acoustic you can see our device has enough horsepower to push fluids from one reservoir to the next reservoir. So I just want to say that our one of the biggest advantage of acoustic tweezers, they have very good biocompatibility. They have if we compare the biocompatibility, if the acoustic wave is on and off, viability per diffraction, pretty much there's very little difference between acoustic wave is on and off versus negative control. So far I give a very brief introduction of the mechanism. I go very little on mechanism. I show a few capabilities, what acoustic tweezers can do. Now I'm going to mainly go to applications, different applications, how acoustic tweezers can impact biology and medicine. So the first example I'm going to show is to use acoustic tweezers to separate circulating tumor cells. So circulating tumor cells can be possibly very important for cancer diagnosis and prognosis and treatment. So theoretically, you can just draw a tube of blood. You can separate these circulating tumor cells. Potentially, they can give you a lot of information and tell you whether this person has cancer or not, where is cancer located, and how early or how late cancer is, and what kind of drugs can be most effective. So it's almost too good to be true. Right? But the difficulty is circulating tumor cells, they're very, very rare. Right? You 1 milliliter blood, you have 1 billion cells, different kind of blood cells, but you only get a few, 1 to 100, sometimes 0, 1 to 100 circulating tumor cells. So how do you find those very, very few cells from a lot of cells? That's a big challenge. So although there are a lot of technologies, especially microfluidic technologies that can do that, we think our technology has a really has an important advantage. So because the acoustic wave is so gentle, it can preserve the integrity of the separated cells, which is important because if your separation process change the properties, then your diagnosis based on CDCs will not be accurate, and your treatment will not be precise. So that's not what we want. But our acoustic tweezers, we think, is probably the most biocompatible technique out there. It's a contactless method. It does not need to label anything. It's contactless. And it's very gentle, very low power. So we believe it can preserve the integrity of separated cells. So we think that's important, and that's really our niche. So the mechanism, again, is very simple. I very briefly go through it. Particles with different sizes or different or different other physical properties, when they go through the same acoustic field, they will experience different forces. So they will go to different, if we design the acoustofluidic devices right, we can direct them into different outlets. So this work show that we can, when we flow two different kind of particles, the green particles are bigger than the red particles. So they will experience larger force. They migrate to the middle. They will both will migrate to the middle. But the green particles, since they're bigger, they migrate faster. They will be collected by the middle channel. And then the red particles, they're smaller. They will be collected by two side channels. So that's how we can separate these, two different size particles. And then we take our technology, we did some refinement. We prove that we can separate cancer cells from blood cells. So when the cancer cells, blood cells come together, and later on, because the cancer cells tend to have different sizes or different mechanical properties, they can be separated. So yeah, this work we're in collaboration with Subra Suresh. He is now at Nanyang Technology. He's president at Nanyang Technological University, and his lab provided very good simulation to us and help us kind of simulate, predict the particle trajectories in the flow. You can see this is the dots. Our experimental results, the shaded area simulation results, that matches very well. And also our lab, built upon Subra's expertise, we also build a very strong computational expertise, which is very helpful because it will help our students save a lot of time when they design their own acoustofluidic devices. And so we take cancer patient samples to separate circulating tumor cells. We found that our devices works very well for breast cancer, for prostate cancer, and also for ovarian cancer. And very recently, we also proved that we can not only separate circulating tumor cells, but also can separate circulating tumor cell clusters, which are basically a group of circulating tumor cells. They're bounded together, and they're even more rare than circulating tumor cells. And I believe because we can improve our device throughput, now we can process 1 tube of blood within an hour. So we can use it to separate CTC clusters. And the second application is to separate exosomes. And we believe that again, this part of the research we think can be very powerful for coronavirus as well. And later I'm going to illustrate why. So exosomes are basically nanoparticles, 30 to 150 nanometers particles secreted by cells. So all kinds of cells, they secrete their own exosomes. So these exosomes, they carry a lot of information. They are messengers between cells. And they are important target for basically to help cells communicate with each other. And so in the last 10 years, really people are, especially biologists and medical doctors, they're very excited about the potential of using exosomes in diagnosis and therapeutics. And the reason is very simple. So for all the kind of diagnosis and treatment based on exosome is like, okay, so if you if there are two parties that are fighting each other, two countries are fighting each other, and one way to defeat your enemy is to kill every enemy soldiers, right? That's very expensive. Okay? But there's a inexpensive way to do that. If you can cut the communication between the enemy soldiers, if the enemy soldiers cannot speak to each other, cannot communicate in any way to each other, the enemies will be defeated without wasting even one bullet. Right? So that's the kind of like how and why exosomes can be very powerful, because they're messengers. They're how cells communicate with each other. Right? So if you can do something, can detect these exosomes and can do something on these exosomes, you can potentially can defeat, can cure a lot of diseases, including cancer and many, many other diseases. And the reason why exosomes are exciting, they are not only be useful for diagnosis and treatment of cancer, but also can be useful for many other diseases. We are working on placenta health. We are working on Parkinson's disease, Alzheimer's disease, and also cardiovascular diseases, but almost all kinds of diseases, because all the disease patients, they have their own kind of exosomes. And if we can separate them and analyze them, and you can do a lot of things about it. And also, exosomes that does not only exist in blood, they exist we already know that in saliva, in urine, and in sperm, and I think it's also in sweat as well. So there also another advantage of exosomes over CTC is that abundant. You in one microliter biofluids, you can have a few thousand to even billions of exosomes, and also the physical property and the chemical property is very stable. But the difficulty is exosomes are very small. They're 30 to 150 nanometers. So separate them is difficult in that aspect. So this is our device. So we have one device. We have two modules. The first module is to separate red blood cells and white blood cells and platelets form, because all the particles above 1 micrometer, we can use our first module to separate them. And the second module is to, and then after going through this first module, and then all the particles will be below 1 micrometer, and they can be directed into different outlets based on their size and different other physical properties. You can see the blood come in, right? And then now they experience the acoustic waves. So they will be directed into the larger 1 micron particles will be directed into this outlet, the cell waste outlet. And now the particles below 1 micrometers, they will be directed into different outlets. One is exosomes. So that's the working mechanism. And we post this video on YouTube, and within 6 months, about 20,000 people viewed this video. So we are very happy. And this is not a basketball game or football game. So we're very happy that so many people are still excited about science. So we also characterize exosomes. We look at the protein expression. We look at mRNA, miRNA, and also the morphology. They all looks very nice. And we prove that this is I think is a nanoparticle tracking analysis data show that if we flow exosomes and microvesicles are slightly bigger than exosomes, right? If we flow a mixture of these two into this inlet, and they can be after going through this our device, the exosome outlet, you can see all the particles are below 140 nanometer, and all the microvesicle outlet, the particles are above 140 nanometer, almost 98%. You can see the separation efficiency, at least from this data, looks very good. And we can not only separate exosomes, but also we can separate exosome subpopulations, because exosome, the size is 30 to 150 nanometer. But within this exosome, there are different subgroups based on the size and other properties. And we can separate them into 3 different kind of groups based on the properties. One is called exo-large, the second is exo-small, and the third is exo-mid. So again, once you separate them into different outlets, and you can do further analysis, you can know which subgroup actually has more impact for certain things. So very recently, we proved that we can, so before we mainly do exosome separation from blood, from plasma, and also from cell culture. Very recently, we proved that we can also separate exosomes from saliva. Right? So you can see the inlet before separation is wide spectrum, after separation, very narrow band, and most of them are exosomes. And I want to stress that our method, and if we compare the yield, our method, the yield is 7 to 8 times higher than ultracentrifugation, which is the gold standard way to do exosome separation. And using acoustic tweezers to separate exosomes really have a lot of advantages, and has it can be we can make it automated process. Because of this, the device will be a lot more repeatable. The process time will be a lot shorter. You don't need a traditional way method. You need 8 hours, sometimes even overnight, a few days. Now you only need 5 to 10 minutes. And the efficiency is a lot higher. Actually, our saliva data shows our efficiency is 8 times higher than ultracentrifugation. And the purity is also higher, from 30% to more than 80%. And most importantly, we think, because our device is very gentle, right? it only takes a few minutes. You don't take a few days. And the force is gentle versus ultracentrifugation. It takes 200,000 G. So it's very, very high speed. That's why you can separate these nanoparticles. And so because our force is gentle, our time is shorter, we can preserve the integrity of the separated exosomes. And here I just want to stress that exosomes, our device, I think now everybody is very concerned, and even some people, including some of my family members, are very scared of coronavirus. I think in the last a few months really changed the world, for better or for worse, mainly for worse. So we think our technology can do a lot to this coronavirus, and here's the reason why. There's a lot of similarities between exosomes and the coronavirus. If you look at the size, exosomes 30 to 150 nanometer, and coronavirus is 30 to 90 nanometer. And also other physical properties also very similar. And the composition is also similar. You have proteins, have other nucleic acids, and they wrapped around, in a kind of a structure. So, and even some biologists say that viruses are one kind of exosomes. I don't know. I think there's always up for debate, but from engineers' point of view, it doesn't really matter, because physically they look so similar. If they look so similar, and our acoustic tweezers is a physical method, right? We can, whatever we can do with exosomes, we believe we can do it with coronavirus. And so why there are already detection analysis technique you can do coronavirus, and why do you need one extra one? And now I'm going to illustrate to you why it's important. Right? So the current method that you do for detection and analysis of coronavirus, you need to have a kind of a device get very deep into your nose. Okay, you get it into your nose. So that's a kind of invasive technique. Patients don't like it. I don't think I would like it. And it could also cause infections to the operators, to the medical doctors and nurses. You can see those people get, actually the infection rate is very, very high, unfortunately. But if we can, we already proved that we can separate exosomes from saliva, and saliva will contain coronavirus if this person has coronavirus. So what you can do is you can collect this sample yourself, right? And you can send it out, and then our device is probably the only technique, a point of care device that can separate these nanoparticles, such as virus or exosomes, within 1 minute. So it's a very simple, very quick, very point of care devices, and we can do it in a very non-invasive way. That's why we think can be important for coronavirus and other kind of virus. If in the future, 10 years later, there's another kind of virus, we think our device can play a very important role. And so the third application is transfusion. Transfusion, again, is a different game. So so after our papers are published, many in the microfluidic journals, we get approached by a transfusion company, and they say they don't care about microfluidics. They don't like microfluidics. They say, hey, you guys deal with tiny amount of fluids. We don't care about tiny amount of fluids. Can you deal with a lot of? They want to process a lot of fluids. They want to do transfusion. Because you can imagine, you want to transfuse the blood in a very short period of time. You want to speed is very, very important. So, and then the kind of speed, the one is tens of to even 100 milliliter per minute. So again, so now the gold standard way to do it is centrifugation. Right? But centrifugation, way again, it could damage the cell components, and later you're going to transfuse the cells for a therapeutic purpose. So that's, if the blood quality is not very good, it causes a lot of complications, and it does cause a lot of complications. And our acoustic wave is more gentle. So again, we proved that we can do very high throughput cell separation. We can do 20 milliliter per minute, and you can see when the whole blood come in, and once we turn on acoustic wave, red blood cells and white blood cells will go to one outlet, and the platelets will go to another outlet. So this particular work, we are separating platelets out from red blood cells and white blood cells. And in another work, we can separate plasma out from all these cell components. And we characterize, and we actually did a comparison between our device with this commercial centrifugation transfusion devices. You can see, although our device is more, is actually, the efficiency is actually higher than the commercial devices, although our device is not optimized at all. And also is more gentle. We can have a better opportunity to preserve the integrity of the cell components we are processing. You can see at different level, at the p-selectin concentration, at the morphology, and also at the platelet aggregation, and at the membrane integrity. Every single aspect, our device shows better promise and better integrity. So the number 4 application I'm going to talk about is fluorescence activated cell sorter. So the first 3 examples are cell separation, but they are separating based on the physical properties. This one is separating based on the chemical properties. So FACS, fluorescence activated cell sorter, is a very powerful technique used in many labs in biology and chemistry. But the problem is expensive, and they have significant biosafety issue, also biocompatibility issue, because they are using high stress, they're using high flow rate, high stress, if you generate high stress to push the cells, and also they use high voltage. So and these results show that the cell viability is for some fragile cells, they only decrease 30 to 99%, which is not good. You don't want it. And our acoustic wave is more gentle, right? And here we are developing a lab-on-chip device that can. So here we are using acoustic wave to focus instead of the hydrodynamic force to focus the particles. We are also using acoustic wave to deflect the particles into different outlets rather than electrostatic force. So by doing this, we can reduce the flow rate by 10 times and reduce the voltage by 1,000 times. Still, we can achieve the same throughput. So by doing this, our biocompatibility is, we think, is the highest. And also biosafety is a lot higher because it's a closed liquid environment. And also our device is small, and we think can be inexpensive. So we proved that we can use it to separate particles and cells. So this one shows that, hey, we can in one device, we can direct sort cells or particles into different outlets, outlet 1, 2, 3, 4, or 5 in one step. So the number 5 application I'm going to talk about is high throughput single cell manipulation. So here it shows that we can, using acoustic wave in a contactless manner, in Chinese, a 隔山打牛的办法, we can bring the 2 cells together. We can precisely control the cell-cell distance, and you can see when the 2 cells are in contact with each other, the dyes will be transferred from one cell to another one. And if we hold them apart by even 3 microns, the dye transfer will not occur. We can not only control 2 cells, but also we can control many, many cells, hundreds of them, thousands of them. At the same time, you can see this, we can control many different particles at the same time. Again, in a contactless, 隔山打牛的办法 manner, in contactless manner. This work shows that we are dealing with biological cells. We believe a cancer cell line. You can see we increase the distance between these 2 cell types, and we bring these 2 cells together, and then later we can separate them. And all this, we can do this in a programmable, contactless, and high throughput manner. So the application number 6 is we can use acoustic tweezers to do tissue engineering and 3D bioprinting. And I think 3D bioprinting has become a very powerful tool out there. Our technique, I think the advantage of our technique, there are two things. Number one is we can achieve single cell resolution. Number one. Number two is we can preserve the integrity of this manipulated cells. So the first generation 3D printing device, what we do is a pick and place method. So we pick a cell and we place it. We pick and place, pick, place, and we are writing 3D AT, which stands for three-dimensional acoustic tweezers. So this is our first generation device. I think is a good illustration, but it's very slow. It's a slow process. So now our second generation, we can print them at the same time. We can print many cells at the same time. We are writing Duke. Again, we have single cell resolution, a very high resolution at the same time. It's very gentle. We can preserve the integrity of the manipulated cells. After 2 days, the cells start to grow. Still start alive and started to grow. So using this to do 3D printing and tissue engineering, I think one advantage is acoustic wave. We can do it in a contactless manner, and we can do it in a programmable manner. Right? We can program. We can change the cell distance. We can kind of form whatever kind of configuration we want without touching any of the cells. So I think that's the advantage that only acoustic wave can afford. I don't think other techniques can really afford it. So we can here you can say that you can see that we are changing the distance between the two cell the two lines of cells, and also we can do pattern translation, pattern transformation. We can rotate the pattern. We can also merge the pattern and change the pattern. So all this work. We can also can control not only one cell type, but also we can control many different kind of cell types. And so now, after arriving at Duke, I think my lab became very conscious in terms of how to do this, make our device more amenable to biologists and medical doctors. We want our tools to be used not only by us. I think if our tool is only used by engineers or physicists, is meaningless. We have to make our tool so simple to use that biologists can use. I even tell some of my students, I say, you need to make the devices so simple that my grandma, who cannot read in English or Chinese, she can use it. Right? So that's something we want to do it. And this is biologists like petri dish. They like multi-well plate. So now we are making our devices compatible with petri dish with multi-well plate. And this work show that on petri dish we can still do acoustic tweezers, and we can form whatever pattern we want. We can do pattern translation and pattern transformation. So the next example I'm going to show you is digital acoustofluidics. Basically, is to do fluid handling. Now, people using robotics in the pharmaceutical companies and other industries using robotics to do fluid handling. They are very bulky, very expensive. They also require physical contact. They need pipette. Right? They need pipette, and also generate aerosols, which is not biosafe. So our device, we can make it more compact and more is contactless. It does not generate aerosol. It also has, we believe, 10 times or even higher throughput and better better programmability. So this one show that we are I'm not going through the physics and just explain that. Just show the results. We are using to program the droplets. We are writing Duke, and each one of them is a droplet. So, and we can do droplets merging. We can do droplets splitting. Again, we do it in a contactless manner. We are doing it in a 隔山打牛的办法. And we also can basically control the reaction. Right? Suppose you have 4 droplets. First droplet one, you can merge droplet 1 and 2 into one droplet, and you merge droplet 3 and 4. You can merge into another droplet, and you can merge these 2 droplets together. Again, we can do it whatever programmed way we want, and we do it in a contactless manner. So the last example I'm going to show is that I want to say that our acoustofluidic devices, our acoustic tweezers, we have so our device is very compact, is very expensive. So that's why you make it very easy to integrate our acoustofluidic devices with other existing platforms, such as cell phone. So now I'm going to just use one example to integrate acoustofluidic platform into cell phone. So why this makes sense? Simple. Acoustofluidic devices very small, very inexpensive. Cell phone is also very small, and also everybody has a cell phone, has a smartphone. And smartphone actually can do a lot of things. Smartphone can do, smartphone can take actually high resolution image. Smartphone can be a very powerful sensor because it has a very high resolution camera. And smartphone, you can have, so you can take a biosample, you can do a detection of this biosample. And you can have apps on your smartphone to process the data. And then you can send emails, the data back to the doctors, to the hospital. And the doctors can send back to your smartphone to tell you, hey, to send you the interpretation of the data. But one thing a smartphone cannot do is, smartphone cannot process fluid. However, that's the strength. That's something that our acoustofluidic device can do. So that's why it makes sense. If we integrate our acoustofluidic devices with smartphone, we can do pretty much everything from sample preparation to detection to processing data and to sending out data. And so very recently we showed that our device we can process undiluted blood. We can use very low power. It only requires a few volts. This is important because if you only need a few volts, you can get that kind of voltage for many compact electronics, including your smartphone. So then you can do many different things. So we just very new in this field. We just we integrate smartphones. So this is a very simple example. We show that we can use our acoustofluidic devices to concentrate nanoparticles and then to improve the detection sensitivity. Then we enable smartphones to capture the data to do detection. So in summary, I have given 8 different examples of what acoustofluidics can do, from separating circulating tumor cells to separating exosomes. We also believe that we can also do it for coronavirus and transfusion, fax, and many different single cell manipulation, single particle manipulation, 3D bioprinting, tissue engineering, digital acoustofluidics for droplet manipulation, and also integration with smartphone to enable really point-of-care devices. And we believe that our device, the advantage of our devices, the biggest advantage we believe, because the power intensity is so low, is only 10 million times smaller than that of optical tweezers. So that which make our device is also similar to acoustic, very similar to ultrasonic imaging. So which make our devices very biocompatible, which we think is a very important characteristic for applications in biology and medicine. And our device is very versatile. We can manipulate particles from nanometer scale to micrometer scale to millimeter scale. And we can manipulate particles within all kinds of biofluids, from aqueous solution to blood to sputum to saliva. And we can manipulate either fluids or particles inside fluids. And we can manipulate a single particle or billions of particles. We can do low throughput, a few nanoliter per minute. We can do very high throughput, 20 milliliter per minute. And we can do translational movement along X, Y, Z axis. We can also do rotational movement along X, Y, Z axis. And our device is very compact, very simple, and very inexpensive. So I want to disclose that I have a few patents on this, and I have co-founded a company, and the university require, whenever I give a talk, I have to disclose this. So again, I'm just, my students, I really cannot speak enough of, the greatness, the excellence of my students and postdocs. They're really my heroes. They did all the work. They make my life so easy that I don't need to do anything except for giving talks. Also want to thank my collaborators. I want to thank all of you for your attention. I think now it's very, very late in China. I really appreciate you sacrifice your sleeping time to listen to my talk. Thank you very much. Thank you.
Great, wonderful. So let's thank you, Tony, again for this wonderful talk. And let's take a look at some questions. Alice?
So I'm working on this. Okay, Shenhe, I'm working on this. Yeah, a second. Okay, you can go ahead. Yeah.
The first question is from Jun Huang from Shanghai Jiao Tong University. The question is, nowadays, microfluidics is developing very fast. And one of the major directions may be the point of care devices. Could you please give more comments on the developing direction of microfluidics? Is there a possibility that the wearable microfluidic devices would involve other detection method in the chips, like acoustics, magnetics, or electronics? How does Tony's view the other manipulation method? Tony, go ahead.
Yeah, so it seems like almost everybody who asked questions from Shanghai Jiao Tong was kind of interested. Yeah, I kind of agree with the comment. I think microfluidics, the field has been out there for 20, 30 years. Really, I think now it's really really time for the field to create more commercial products that people can really benefit from this. And if you want to pick a time to do that, I think there's no better time to do that than now. Right? With this coronavirus widespread almost across every country, I think people will realize having a point of care devices, having a devices which is very simple, very inexpensive, very portable, and very easy to use, and can deal with very simple biofluids such as saliva, urine. I think is extremely important. I think people will understand this. And I mean, there are many reasons that in the past 20 years we have not done too much on this. I mean, we have not made enough progress on this. I just feel that the industry and the academia is disconnected. I think people in academia, I think my group, certainly myself, is also guilty for that. We do things to publish papers, right? We don't do things to, when we do things, develop technologies, we don't have the end goal in mind. How can our research benefit, push the better, make our life better, make our grandparents' life better, make our grandchildren's make our grandchildren's life better. I think that's something I think people as academia, I think we need to do a better job, including especially my group, myself, do a better job on that. And I think also the investment, to do this, it really takes a lot of time. It takes a lot of time to get it done. It takes a lot of time, takes a lot of money to do that. But it can be done. I'll just give you an example. Inkjet printer, right? So it's a very complex microfluidic devices. It was invented in the, it was invented, commercialized, and benefited so many people. But the reason why it was done because HP really wanted to get it done. They invested a lot of money. They put a lot of good engineers to do that. But if you look at inkjet printer, the device actually is a lot more complex than a lot of the microfluidic devices I'm presenting today. Okay? It's more complex, but they're commercialized. I think they just yeah. So I feel that for this, I think now is a good time because with coronavirus, I think probably make microfluidics, make people beyond microfluidics realize really microfluidics can do a lot more than it has done. And I think that the fact that we get Jun, get interested in microfluidics, I think is a very good example. I think Jun has been very, very famous in many other fields, and the fact that get him interested in microfluidics, I think is very good for microfluidics. I'm very happy to see Jun doing microfluidics, and Jun also has a postdoc that going to join. Xiaoyue Ni is join Duke. I think I'm going to work with her. I think there are a lot of things I can do with Xiaoyue, and so absolutely, I think the some of the manipulation technique, including our technique, acoustic tweezers, and also some of the other technique, can be integrated into Jun's platform and other people's platform. And I think together, everybody just, again, have to work together. People in academia, people in industry, also with government, encouragement, funding from government, and also the people from different fields, people like Jun, like myself, and many other people get into this field. I think there's no reason that we cannot make an impact. And all the, I don't see any any reasons in physics that cannot be solved. I think all the physics has been solved. It's more like engineering problem, biology problem, but they can be solved.
Great, wonderful. We see the passion of Tony based on solid technology. Now, the second question is from Harbin Institute of Technology. The question is, we know that it's difficult to obtain high precision in particle manipulation using acoustic wave, but nanoparticles can be manipulated in your work, Tony. The question is, the student would like to ask you how nanoscale particles are controlled by acoustic streaming flow or radiation force. So this is a technical question, Tony. Go ahead.
Yeah, so basically for all the manipulation, I think it takes, we are using either one, typically a combination of two different forces. Number one is acoustic radiation force, the other one is acoustic streaming. Right? So manipulating nanoparticles is a challenge, right? But it's a challenge, as you can see from my presentation, can be addressed. Right? We are manipulating particles as small as 20 nanometers. So we believe we can go even smaller. We believe we can push to 1 nanometer. And maybe even smaller. I actually told one of my students, if they can manipulate the particles as small as 1 nanometer, I can let him graduate. So I think people who work in this field, acoustofluidics field, we have to be open-minded, right? We have to be aware of what's going on in other fields. So, for example, I think the people who work on acoustic metal materials, acoustic metal surface, they already have done a lot of fantastic work. They already have very, very innovative concepts. We just need to learn from them, adopt some of the beautiful physics they already done into our platform. Right? And I think we can not only manipulate particles as small as 1 nanometer, but also can do a lot of things we cannot do. For example, so now the acoustic tweezers, the precision, I don't think the nanoparticle manipulation is the biggest problem because we already proved it works. I think the biggest problem is to achieve very high resolution. Now our resolution is probably about 1 micron, which is much, much worse than optic tweezers. But I mean, the reason is simple because the frequency we have used is much smaller than optic tweezers, but it can be solved. Right? So I try to challenge my students also, if we can, I want them to be able to do everything using acoustic wave to do everything that optics can do, right? In addition to that, beyond that, because acoustic tweezers really have some advantages that optic tweezers will never have. Even optic tweezers will never have the kind of biocompatibility we have, and they will almost never be able to be as point of care as acoustic tweezers. So if we can reach the kind of resolution and the kind of very, very small scale manipulation as optical tweezers, even better, I think we can make a tremendous impact. And we can really grow the field. Now it's a very small field. It's really acoustic tweezers or acoustofluidics. It's a very small field. Very few people work on this and very few people are interested. But I really hope more people can be interested in this.
Very good. So the next question actually is related to resolution. This question is from Gong Zhixiong from IEMN CNRS France. The question is, I'm very interested in the application of standing waves, which your group has done a lot of great works to me. However, the standing waves have multiple modes or antinodes, hence leading to the failure of the selectivity of the beam. Could you give us some suggestions if we want to pick up one cell from a cluster? Tony, go ahead.
Yeah. So so again, it's a very good question. That's something we are working on right now. Also, I cannot reveal too much of our secret because we have not published anything on that, right? But that's a challenge. I think the other groups are doing actually way ahead of us. Bruce Drinkwater's group in UK, they're doing many. I think in terms of single particle manipulation, I think they are leading us by many miles. So I think the student can learn a lot from Bruce Drinkwater's work. They have done wonderful work. They have the capability to pick one cells from many cells without affecting other cells. So I just say that, you know, again, that's something I think if you are students, I'm very happy that you know, Alice using this platform, because this is not a microfluidics platform. It's a much broader than microfluidics. You bring so many people, I think smart people into this, and I hope that some of them listen to my talk and they say, hey, I have an idea how to do that. Right? So I just because if you think about it, right? So why it's difficult? Because a lot of physics involved, acoustics involved, fluid mechanics involved, and also how the particle behavior involved. So if you, I think the combination is difficult, but if you can get people who kind of know one aspect working together, I think a lot of these problems can be solved. I have seen that again in my own laboratory, and also seen other people's laboratory, and I think I'm gonna see a lot of that in the future.
Very good. So the next question is from Zhengfeng Yi of Peking University. Thank you, Tony, for your great talk. I noticed that the applications in your presentation are in vivo experiment on chips. How long will it take for acoustofluidics to be applied in vivo, such as blood vessel or tissues in the body? How to solve the influence induced by the change of the media from silicone glass to tissues? For example, perhaps fat and body fluid with complex components will decrease the accuracy and the carrying capability of acoustofluidics. Tony, yeah, this is a challenge.
Again, that's a very good question. And if the student asks me how long it's going to take, I really don't know. I cannot. I mean, yeah, I'm not as smart. I'm not smart enough to tell that. But one thing I want to say that. So now we mainly do it on in visual. That's just because our understanding is very limited. However, I think doing in vivo is exactly what the advantages of acoustic tweezers or acoustofluidic, because as I said, acoustofluidic is a 隔山打牛的办法, right? So we can actually get into your body. Actually, we can not only get into your body, we can get through a mountain, right? If you can get through a mountain, you can get through your body. No problem, really no problem. Okay. But the problem is we don't now at this moment we don't understand the body. Okay, we don't understand the acoustic wave that well, so we still have to kind of play with on a chip format. But once we understand it, once we get enough smart people work on this, I think that's well acoustofluidic field can be as popular as John Rogers' field. Okay, now it's not because nobody cares about this. I just feel, but if we really can do in vivo, maybe our field can be even more popular than John Rogers' field. I hope John is happy with this. We can diagnose a lot of disease. We can treat a lot of diseases because acoustic wave, we can get into the body without touching anything. We can get into your scar. We can get many deep part of the body. We can get into your prostate. You can get, so I think that's just take a lot, but it takes generations of work. But the challenge now is the number of people who work on acoustics is very small, okay? And the people who work on this field and the number of people who do acoustics with interest in acoustofluidics or biomedicine is even smaller. That's why we are slow, but we really think tremendous potential and prospect in this field.
So the short answer is please join this field. Tackle
this. Exactly. That is.
Yeah.
The 8,000 people listen to the talk. I wish 10% of them, 800 of them in this field.
Very good. The last question in the interest of time is Wang Fang from BINN, University of Chinese Academy of Science. I would like to ask a question about the non-contact acoustofluidics. What kinds of problems are still waiting to be solved? For example, if the material are inducing the polarization of electrostatic interference, what are the potential research directions in the future? Tony. Again,
Yeah, so
calling for leaders' answer.
That's a good question. So we tend to, when we work on research, we tend to only consider acoustic effect, but there are many other effects such as dielectric fluorescence, other effects we just have to, we also have to consider. I mean, again, it's just there's still, again, I just go to my, I answer a lot of questions, but eventually I only go to one point. And one point is, there are a lot of physics problem, engineering problem, biology problem has not been solved, and we need smart people to get into this field and to solve these problems. And if that person, a student, is more interested in, I have some papers published in coupling acoustic wave and DEP, and we have a few other papers in pipeline, and they can read my papers.
Great, wonderful. Now I think Alice will have final comments on this talk. I think this is a greatly successful. Alice, go ahead. All yours.
Yes, it is always great, to hear Tony's talk. I think, Tony every time give everyone, very encouragement. You see him, is like a superstar. Yeah, I always wondering, a few weeks ago, I read an article. I say, okay, Tony always ahead, advanced. Why? Why? The question is why, he's super smart and he is super, but another thing later I found out, he has super, kind of mentors and supervisors. So Paul Weiss, are you here? Yeah, Paul, are you here? Can you turn on, Yeah.
Still here.
Okay. Yeah, still here. Paul is now in UCLA, but at Penn State. He's Tony's mentor, right? Yeah, he's Tony's mentor. Can you give a few words for Tony? Yeah, see how Tony grew up like this?
Tony makes us all proud. He's incredibly enthusiastic, creative, and productive, and he was actually introduced to me as he arrived at Penn State by Fraser's daughter, who was here and wanted to work together with us, and said Tony would be the perfect collaborator for us to have. And so just as Tony arrived, we started working together, and then his terrific first student, Yubing Zhang, was also incredibly productive and moved from Penn State and joined us at UCLA when I got Fraser's job here as Fraser moved to Northwestern. So we've been working together ever since, and actually we have a paper under embargo together on acoustofluidics at PNAS now, and I was just working on another manuscript with Tony a few hours ago that we're hoping to submit shortly. So you'll see a little bit more of the collaboration in the talk in a couple of weeks. Thanks,
Okay, great. Yeah, Paul, yeah, it's also our speakers will come out, weeks later. So you're looking forward to his talks. Another thing is, I think, Tony was such a superstar, not grow up. Where he grew up, when I go through all this background, I found someone is very important in his life and in his career. So because this one was so famous, and this one was so important and so special, he's much more famous than everyone here because he was highlighted as the best scientist, in China. He also was get on a big platform show, and he's quite famous on all this. Who is this one? Who is looking for, a nursing Tony to grow up? Now we give him our secret guest, okay, our best VIP. So are you here? Can you turn on the video? Okay, let me see. Hi, Tony, see.
Hi, Alice.
Hi, 唐老师，非常非常感谢。Okay, Professor Tao, yeah, he's get on the Chinese CCTV show, and it's the best, after 80s beauty, right? Yeah, the internet celebrated, internet, stars, 80后网红, the best teachers, all this and all this. So Professor Tao, please tell us some stories about Tony. Okay, welcome.
Okay, Alice, I will speak in Chinese.
Yeah, sure, no problem.
你今天晚上讲课很成功，我和你的许多师兄弟都在听你的课。 而且为你感到高兴。从你1996年西安交大少年班毕业以后，见到我们工业物理专业工作硕士学位，我有幸成为他的硕士生导师。他在西交大的期间就表现非常的才能。1999年去美国 UCLA， 贺志明教授指导下攻读博士学位，名叫 MEMS 理论跟技术。我博士学位以后，在声流控技术方面取得杰出的成就，获得了很多大奖。今晚讲课的大部分内容都是他自己研究心得。Tony，我代表母校预祝你今后取得更大的成就。西安交大正在为创建世界一流大学而努力。2019年，中国西部口长兴港建成并投入使用，为广大青年发展提供了广阔天地。学校正在全世界范围里面招聘青年教师来西安跟我们发展，这方面也希望你的支持跟帮助。我代表母校谢谢你。
Okay, good. Thank you, Tony. Did you have words to your mentors and supervisors?
非常感谢，太感谢陶老师了，我这非 surprise， 我不知道陶老师会出现，就是非常 surprise， 真的非常感谢陶老师。我觉得陶老师，我觉得我如果非常感谢母校，然后我觉得我如果这辈子能做的事情能够到陶老师的1%，我就非常满足了。我觉得陶老师这个以身作则，这个80多岁，然后比我们所有人都要勤奋，我觉得太值得向陶老师学习。我希望我这个能够这个以后能更像陶老师一样，我觉得绝对是做不到，但我希望能够更像陶老师一样，然后我希望我的学生也能够更像陶老师一些。谢谢陶老师，非常感谢。对，
谢谢。
Okay, great. So yeah, Tao老师, thank you very much. Okay, I have to say that when I heard you can, watch all this kind of online show till the 11 o'clock, I was moved very much too. I think, okay, that's really a big demo. Tell everyone on the line here, how to do be a best scientist, do a good scientist, do research. You have to be hardworking. Professor Tao is a big demo, and for all of us, more than 80 years old, he was still working till the midnight. He do all these things dedicated, everything prepared so good. And he was also very interested in all this high tech. He's even more fashion than us. Everyone has, if you double check on the internet, you will see that 80后网红老师 ，so 院士，你马上就会搜到唐老师，他也是上过我们的这个开讲了的嘉宾，所以你会看到唐老师是如此的努力。那在过去的可以说是60多年的时间里面嘛，唐老师一直是战斗在一线，是各行各业的，就是不管是教学还是科研，还是育人，还是在做事这方面，都是我们的 big demo。所以我觉得我们现在应该给唐老师最热烈的掌声。OK，
谢谢爱丽丝。
陶老师，我在这里也真的是特别的诚挚的邀请您，如果在您方便的时间，在一个周五可以来给我们讲一次。尽管我们比不上开讲了的舞台，但是我们真的是用全世界的同学在播的一个舞台。OK， 我想你给大家更多的 encouragement， 给大家更多的这样的good demos， to show everyone。OK， 我真的诚挚的邀请您，您考虑一下。OK。
谢谢。
Okay, that's great. Now it's going to the last part to, have our great show. So now it's Tony's certification. Tony, I see that just now, we delivered #1 to John Rogers. So now you are #2. But I think next time you will be #1. Okay, answer my email in seconds. Okay, no delay. So this is for Tony. So Tony was, tell everyone how the technology changing the world. And he's changing the world. He's not only working in the academic, he's also, help to get collaborated with the industry, even set up his own, startup company, try to, help the whole world. Let's get more things done to help more people. I think that's the best word and we can give to Tony. Tony, thank you very much. Okay, that's for you. I will deliver to you later. Okay. Okay, cool. So now everyone, we are really great. We keep our time. I know it's really late. Almost 11 o'clock. Thanks for keeping in this online show. So the ICANX talk just start. So what will go on next? So let me see. Yeah, we're already full of the schedules. See, next May, next month, we're already full the schedules. Yeah, in May, we have the speakers, on this line. Paul Wish, as Tony's mentor, now is a silver star, he's doing a lot of nice work. He will come on and May 1st. Then May 8th, we have Nick Fang from MIT, Gao Wei from Caltech. And May 15th, we have a Professor Suo Zhigang, he's very famous, very big stars and super lecturers, speakers from Harvard. He will deliver talk for us. And May 22, we have Hu Liangbing and Yu Chunjiang, all these two young, super young stars. You will see, like Tony is doing everything, exciting and doing a lot of things, especially for the biomedical stuffs. Yeah, they are going to get, have more people in the hospital. And Gu Zhen will come out and May 29. So this was the list for the May. But who will be next week, right? Everyone, so who will be next week? Okay, let's see. Our next week is a super star. I love it very much because Xuan He was doing so many good jobs. He's our guest, host today. You see that he's really good and he doing a lot of things. This was a speaker, so you see how excited, can cheer you up and can encourage the whole field, not only his research and of course his energy. So next week, we will have Xuan He to tell us about his stories. Is for all these kind of new things for the soft materials, for all these soft material to be used for the machine and human interface. How all this can be, get involved with ourselves, and how this feels to be changing the whole world in the next week. So we couldn't wait till next week. Next Friday, 8 o'clock, I see you on ICANX Talks. Yes. Xuan He will come out. So next Friday, be sure, come to ICANX Talks and keep together with ICANX Talks. It's a good time to link you with the world. It's a global online science show. We tell everything new, everything latest. Okay, let me stop here. I see you next Friday for ICANX Talks. Okay, thank you very much.